Hello everyone, myself Ashish Rai, and this video is a part of exam paper solution of analysis and design and algorithm. This is a solution of end semester paper. So let's start from the question 1. Question 1 is analysis the time complexity of quicksort algorithm in average case and provide a step-by-step explanation of sorting process. So the right answer, time complexity of analysis in average case. In the average case, quicksort exhibits a time complexity of big O of n log n. As we all know that its time complexity is n log n, where n is the number of elements in the array, and this considered efficient and make quicksort one of the fastest sorting algorithm in practice. Step-by-step explanation of sorting process. First of all, choose a pivot, then partitioning, and then recursive call, combine, then repeat until the sorted. So choose a pivot, select a pivot element from the array. Choice of the pivot can impact the performance of the algorithm and different strategy can be used. Example, choosing the first, last and middle element, partitioning, and rearrange the array such a way that all elements less than the pivot are placed before it and all elements greater than the pivots are placed after it. This step ensures that the pivot elements is in its correct sorted position. Then recursive calls. Recursively apply the above two steps to the subarrays on the left and right of the pivot. This means repeating the partitioning step for each subarray until the entire array is sorted. The recursion ends when the subarray contains only one element or are empty. Then combine. Since the elements are rearranged in the place during the combine partitioning step, no additional combining or merging is required. Repeat until sorted. So repeat steps until 1 to 4 until the entire array is sorted. Each step the pivot element is placed in the final sorted position, reducing the size of the subarrays that needed to be sorted. Then question number 2 was critically evaluated Stetson's matrix multiplication algorithm and compare its time complexity with the traditional matrix multiplication methods. Answer may be Stetson's matrix multiplication algorithm is an that's aimed to reduce the time complexity of matrix multiplication compared to traditional methods. It achieved this by using the recursive approach and dividing the matrix into the smaller sub-matrix. However, while Stetson's algorithm provided theoretical improvement in the time complexity, it is a practical limitation and it is not always faster than the traditional method. Here is a critical evolution of Stetson's matrix multiplication algorithm. Advantages of that: reduced time complexity. Stetson's matrix algorithm has a time complexity of log n की power log 2.81, which approximately n की power 2.81. This is the improvement over the traditional matrix multiplication, which has a time complexity of big O of n की power 3. Using the straightforward approach, efficient for large matrices, Stetson's algorithm is particularly effective when dealing with the large matrices, as the reduction in the number of multiplications can significantly reduce the overall computation time. There is some disadvantages and limitations of that matrix algorithm also. Overhead. Stetson's algorithm introduced additional overhead due to the recursive calls and matrix additions. This overhead can offset the benefits gains from the reducing the number of multiplications, especially for number matrices. As a result, the traditional methods can be faster for the small to the medium size matrix. Increased memory uses. Stetson's algorithm requires additional memory to store the submatrices created during the recursive process. This increased memory uses can be problematic for the large matrices, as they may exceed the available memory capacity. Comparison of time complexity, as we have compared the time complexity of both with traditional and Stetson's matrix. Traditional contains the n की power 3 and Stetson's contain n की power log 2.81. Sorry, n की power 2.81. In practice, traditional matrix multiplication algorithm can outperform Stetson's algorithm for the smaller matrices due to the overhead and extra arithmetic operations involved in the Stetson's approach. Stetson's algorithm becomes the more advantageous for the larger matrices where the reduced number of multiplication overpaid the additional overhead. Question number 3 was evaluate Prince algorithm for finding the minimum spanning tree and provide a real world scenario where it can be applied. Answer was Prince algorithm is a greedy algorithm we use to find the minimum spanning tree. MST is a weighted undirected graph. It is start with a single vertex and grow the MST by iteratively adding the sorted edge that connects an already included vertex to an excluded vertex. Here in evaluation of Prince algorithm and real world scenario where it can be applied. There are some advantages here. Efficiency. Prince algorithm has time complexity of big O of v power 2. V is a number of vertices with adjacency matrix representations and big O of e log v. E is a number of edges with the adjacency list representation where v is that we have already covered. Guaranteed minimum spanning tree. Prince algorithm guarantees the construction of minimum spanning tree. Resulting tree has the minimum total weight among all the possible spanning trees in the graph, ensuring optimal connectivity. Suitable for distributed system. Prince algorithm is well suited for the distributed systems as it can easily parallelized. Each node can independently compute the minimum weight edges connected to it, making it efficient for distributed implementations. Then real world scenario. Telecommunication began use in telecommunication network planning. A real world scenario where Prince algorithm can be applied in the telecommunication network planning. Consider a telecommunication company that want to establish a network infrastructure connecting multiple cities with the least amount of cable users. The cities can be represented as the vertices and the cable required to connect them can be represented as a weighted graph. This is the example, few examples where we can see the Prince algorithm is working. Question number 3. Analysis Hamiltonian cycle and provide an example of how they can be used in a real life application. Hamiltonian cycle path is a graph that visits every vertex exactly once and end at the starting vertex. In other words, it is a closed path that transfers all the vertices of a graph without repeating any vertex except for the starting vertex. Analysis of Hamiltonian cycles, NP completeness, exhaustive search, and optimization. NP completeness. The problem of determining whether a Hamiltonian cycle exists in a graph is known as NP complete, which means it's computationally challenging to find an optimal solution in the polynomial time for the large graph. Exhaustive search means due to the NP completeness, finding Hamiltonian cycle often requires exploring all possible paths, making it exhaustive search problem. As the number of vertices increases, the search space grows exponentially, leading to the computationally intensive optimization. While finding a Hamiltonian cycle is challenging, optimizing the cycle for a specific object, example minimizing distance and maximizing efficiency, can be approached using the heuristic algorithm or the approximation techniques too. Real life application of Hamiltonian cycle is that traveling salesman problem. One of the significant application in the TSP involve finding the shortest possible route for the salesman to within the given set of cities and return the starting city covering all the city except one. Question number 4 was derive the time complexity of iterative and recursive version of Fibonacci and compare their efficiency. Iterative, first of all we will see the iterative Fibonacci function. The iterative version of Fibonacci functions calculate the Fibonacci sequence iteratively using the loops. This is the code. First of all, define an iterative Fibonacci function and passing the parameter n. Then first this is a condition: if n is less than, return n. Less than equal to, then return n. Else a and b equal to 0 and 1 for range 2 and n plus 1. This is what actually we are returning b and swiping them. Time complexity of iterative Fibonacci function is big O of n. And recursive approach, this is a base condition: if n is less than 0, then return then, else return recursive function n minus 1 plus recursive Fibonacci n minus 2. Here we are calling the same functions 2 times and adding them. Time complexity of recursive approach is recursive approach has time complexity okay big O of 2 की power n. It is a exponential actually. Question number 5 is non-deterministic search and non-deterministic sort algorithm. Non-deterministic search algorithm do not follow a specific deterministic path but explore multiple possible paths simultaneously which hope to finding a solution. One such algorithm is NDFS, depth first search. Okay, here is the pseudocode for ND, non-determinate depth first search function. This is the function where we are causing problem state. If problem dot is goal state, return state. Else for each actions in problem action states new state equal to problem dot result state actions result NDFS problem new state. If the result is not none, return results, return none. Non-deterministic sort algorithm. This is a non-deterministic sort algorithm. In actually what we are doing, we have an array and taking one element from that array at a time, then copying the same element in the another array and expecting that we get the another array a sorted one. This is a non-deterministic bubble sort, but I have told another example. Analysis question 5. Analysis and compare the P, NP hard and NP complete problems and provide example of each. Discuss their significance in the computer science and their potential in the real world application. In the computer science, the complexity classes P, NP, NP hard and NP complete play a fundamental role in the understanding the difficulty of computational problems. Here is the analysis and comparison of these complexity classes along with the example and their significance in the computer science and real world applications. What is class P? Polynomial time. P is actually stands for polynomial. A problem is class P if there exists an algorithm that can solve in a polynomial time, meaning a running of algorithm is bounded by a polynomial function of the problem size. Significance. What the actually significance of class P? Problem in P have the efficient algorithm that can solve them a reasonable amount of time for the large inputs. They are considered computationally tractable and form the basis for the many practical applications in the area like data processing, optimization and algorithm design. Then non-deterministic polynomial time, that is class NP. A problem in class NP if a proposed solution can be verified in the polynomial time, while NP stands for non-deterministic polynomial, it does not necessarily mean that the problem NP can be solved in the polynomial time. What is NP hard? A problem is NP hard if it is at least as hard as the hardest problem in the class NP. In other words, NP hard problem is as difficult as or harder than any problem in NP. NP complete problem. A problem is NP complete if it is both in class NP and is NP hard. NP complete problem are the NP hardest problem in NP, and the solutions to any NP complete problem would imply a solution to all NP problems. Example of NP hard problem including the Boolean satisfiability problem (SAT) and the knapsack problem, traveling salesman problem. Significance: NP complete problem are of utmost importance in the computer science as they represent the most challenging problem in the class NP. That was the solution of all the questions.